Okay, reset. We just defined the force due to a magnetic field on a charge. And I do want to point out is that there is sort of an overall encompassing thing you can write, what's called the Lorentz force. So this is the force that appears on a charge is QE plus QV cross B. And that, the reason it's grouped together like that is ultimately we're going to get to the point where we say the electric and the magnetic fields really are kind of the same thing. They're just different manifestations of the same effect at some point. All right, but for the moment they're separate. Basically this is a thing for if you want to go into physics. But the reason I mention it here is because you can have both electric and magnetic field effects. And I want to talk about the few places where you see interesting stuff come up, where you deal with both of those. And one of those is a homework problem. We talked about, this is problem 4 on the WebAssign, what's called a velocity selector. What I'm going to tell you about instead is how televisions used to work. And we don't need this stuff up here. So what I'm going to do is just propose. We have some, we have some electric field and some charge. And I'm going to ask what happens to the charge as it goes along. So I'm going to put in electric field here. And then I'm going to put in a charge, positive charge, and we're going to give it a velocity this way. So in the case of the electric field, the force that we see on this thing is along the electric field for the positive charge. That means that this velocity is constant in this direction and it accelerates in that direction. And so the path that this charge is going to take in this electric field is a parabola. Right? When you send at some angle, it's still going to accelerate it in the direction of the field. Now, there is an acceleration here, and that means this charge will get faster. It'll have a higher kinetic energy. So I'm going to mention this is a way of accelerating particles with electric fields. Now, off to the side over here, we're going to do the other version of this. We're going to put in a magnetic field. And we're going to put in the same charge. But as you remember, when we talked about this, there's a right-hand rule. All right, and the way I've drawn it, the velocity is up and the field is that way, and so I'm going to push into the board. The net force on this is going to be into the board here. That's going to end up causing it to rotate a bit. I'll show you what I mean by I'm going to draw. This is not B, this is F. So I'm going to draw this slightly differently. I'm going to draw the magnetic field into the board instead. All right, so into the board is, if you remember, is X's. I'm just going to put X's here. Your textbook may do this. Now, when we do right-hand rule on this, my thumb is up, my fingers are going into the board, the charge is going to go to the left. So I'm going to put it over here so I have space. And I just noticed that a massive grain truck is driving by. And I have no idea why. Like we're a quarter mile from the road. So, you know, weird stuff happens. I cannot get away from the birds that distracted me at school. So, right now, right-hand rule, velocity is up, fingers are into the board for the field. It's going to go to the left. And so we can imagine, it steers it. Now my argument is when it gets here, the velocity will be that way. And we'll do right-hand rule for that. Velocity is that way, field into the board. The force is going to be downwards. This is a circular path. All right. So if the charge moves on a circular path, the velocity stays constant. And this is going to work until I'm out of the magnetic field. All right, as long as the charge is in the magnetic field, it's going to circle the magnetic fields. And it's going to have a constant velocity. And that means the kinetic energy doesn't change. There's no potential energy here. So magnetic fields do no work. This is unusual. Electric fields do work. And the reason that we define a potential energy for them is because we see the work they do, right? Gravity does work, so we define a gravitational potential energy. Because it has a conservative force. And the electric force is a conservative force. The magnetic force, I'm not making any claims about it. The kinetic energy doesn't change because it doesn't do any work. The work, so to be clear on this, if we look at it very carefully here, say this is our delta x. So the work is F dot delta x. But the force is to the left. Right? This is at right angles. And so that dot product is 0. Now I said I was going to get to how televisions work, but that's going to have to wait for the next video.